Welcome to our final demo for SPUD, Single Core Processor Unit and Display, by Mohammed Musa, Frank Laterza, Gabriel Saborito, and Valentina Terry. What is Project SPUD? An educational CPU system that transforms C programs into real-time visual outputs, allowing users to observe how software instructions directly translate into hardware behavior. Modern processors are fully optimized and difficult to inspect, so SPUD proposes a custom modifiable, demonstrable, and accessible CPU for educational and entertainment purposes. It can be controlled in both hardware level and software level. C programs can run directly on the FPGA-based CPU using a custom software library called SPUDKit. Our CPU and system on a chip are implemented using Verilog, allowing us to create custom peripherals like our matrix core that drives our 64 by 64 RGB matrix, and also our arcade controller, which is the main interface for our interactable demos.
Here we have the final product of SPUD. Right here is our FPGA with the peripheral hat on top that's controlling the matrix and the controller. The LED matrix will run all of the demos and showcase them, while the arcade controller will control those demos. This is a 3D model of the design of SPUD. We designed and printed a platform with standoffs for the matrix, and this will also house the FPGA with our main PCB. And then we also printed an enclosure for the arcade controller to hold the bottom of the buttons and the wiring.
Welcome to a demonstration of SPUD. I'd like to show you a quick overview of what we've been working on and jump right into our workflow and how we develop code for SPUD. So if you can see in the corner of your screen here, I have the matrix as well as the arcade controller, and you can see this cable goes right underneath and connects to our FPGA. There's a layer here, keeps it nice and tucked in under there and clean. So the first thing we start with is our Vivado. So this helps us develop all of the Verilog and hardware description language for SPUD, and helps us generate bit streams for the FPGA. This is essentially our core and runs our hardware. We developed many of the modules that you see here in this hierarchical design. The first thing we start with is our synthesis. So we synthesize our design, and we get a good overview of like how much hardware we're going to need, what kind of hardware we're going to need. And we also like to generate this RTL schematic view where we can get really good insight into many of the modules that we develop for SPUD. You can see like this one is the SoC here. We can kind of see all the connections and dive into what exactly is going on. It helps us understand a bigger picture. Then we jump into the implementation. This will route all of our pins and connections and wires. And then finally, we have the our hardware bit stream. So I already have a synthesized and implemented bit stream. I'm just going to open the hardware manager and load up a new version of our SPUD SoC. Perfect. So now our FPGA has loaded the appropriate bit stream such that it will run our SPUD code. So now that we have a CPU ready, let's jump into how do we write code for SPUD. So code for SPUD is very unique, and we have our own chain setup. So I'd like to start with SPUD-env, which is basically our environment for SPUD. This allows us to easily build, load, run, and simulate any piece of code that is built with SPUDKit. So this SoC right here on top is what we were just looking at in the Vivado, but these RV32i tools is what I want to get into on this portion. So we have under SPUD-env, we have awesome tools that we can use. Let's build our first program. So I'd like to show you Hello World, the very first program. So let's build Hello World. Using SPUD environment, we have a build script, and we can pass in the name of the project called Hello World. Pressing enter, we run our tool chains and cross-compile a version of RISC code that is developed for SPUD. So next, now that we've built our SPUD, let's figure out how do we run it. Under SPUD-env, we have a run tool where we can do run hello world. This will load the program onto the FPGA, and we can see under the UART console, it will print out hello world. Very cool. Let's show some other demos. One of my favorites is this donut program here, which we will build together. Once it's done, we can run it. We can see in the corner, we have our matrix running with a 3D spinning donut. What's really interesting about this program is that there are no floating points. You might be asking, how are you doing 3D rotation matrices and all of these decimals that you see in here without floating points? Well, that's because we use a fake float. We basically simulate it via software, since again, our FPGA has no floats, only integers. Moving on, I'd like to show another program. It's Arcade Display, and we'll show a quick demo of how we can test our controller here. So once that's loaded onto there, you can see we have these colored boxes that coordinate to specific buttons that we have on our arcade controller. This is our CPU, which is corresponding with our controller and can update the screen simultaneously. And this is all written through code. It's a very, very simple piece of code.
This is the SPUT demos menu. The user will be able to use our custom-made arcade controller to select their desired game. All of these games are custom-made using our own made library called SPUTKit. And now I'll showcase the snake game. First, we're selecting using this button, and as you can see, I can control the snake to eat fruits. And if I do collide into myself, I can do that now, I will die. And I can reset and go back to the main menu. For our systems engineering specifications, we chose to highlight the following overall metrics: a processor's performance of 10 or more MIPS, an arcade button latency of less than or equal to 30 nanoseconds, an LED matrix refresh rate of less than or equal to 200 Hz, functionality including arithmetic, jump, and memory instructions, a board power consumption of 36 watts, an LED display power consumption of 20 watts, operational conditions with an ideal temperature range between 68 and 77 degrees and a humidity level between 40 to 60%. And finally, a total price range between the range of 300 to 500 USD. For this demo, we chose the processor performance, arcade button latency, and LED matrix refresh rate to be our demoable metrics.
Our first demo for SPUD involves measuring processor performance using MIPS calculations, or millions of instructions per second. We ran two tests, a software test and a hardware test, to accurately confirm our calculations. In the software test, we used a simulation and ran sample C programs that would toggle an LED every n number of instructions, whether that was 1,000,000, 500,000, or 2,000,000, using a loop enrolling flag in a compiler, just to make sure that we were getting the exact number of instructions that we wanted. For the hardware test, we used an oscilloscope that was connected to a GPIO flag on the FPGA and programmed that to be set anytime an LED toggles, and we used the same sample C programs as the software test. Our first simulation test involved running 1,000,000 instructions and calculating the time it took between the starting of the toggle and the ending of the toggle. After figuring that out, we divided the number of instructions by that value and got 18.2 MIPS. We repeated this test, but this time with 500,000 instructions. We did the same calculations and also got 18.2 MIPS. Once again, for the last test, we ran 2,000,000 instructions, calculated the delay between the toggles, and lastly, divided it by the number of instructions, and we got 18.2 MIPS yet again. Here is our hardware test setup for the MIPS test. As you can see, it's connected to a GPIO pin on the FPGA, and then we have each box here represents 10 milliseconds, and you can see we have 55 milliseconds. Using the same oscilloscope configuration, we repeated the test, but this time with 500,000 instructions. On the screen, you can see that each grid represents 10 milliseconds. If you calculate the distance between the first toggle and the second toggle, you get 27 milliseconds, which is exactly the same as what we got in simulation. For the final test, we ran 2,000,000 instructions and measured the delay between each toggle. On this screen, each square represents 50 milliseconds, so it looks to be about a little over 100 milliseconds. After running all 10 tests, we were able to verify that the hardware and software we're both able to get the exact same results, and we calculated 18.2 MIPS for both.
For our LED matrix refresh rate, we used both a simulation program and a physical setup in order to measure the delay between each full screen update. A full screen update is updating 32 addresses, which corresponds to all 64 rows on our display. After deriving said delay, we then take its inverse to get the refresh rate in Hertz. We are going to start by simulating the setup and using a flag that toggles between each full screen update. Then we will use an oscilloscope in order to measure the same flag toggle on the actual hardware. As you can see with the simulation, our delay between each toggle came out to 6.65 milliseconds. And for the hardware, each toggle we see on the oscilloscope takes around 6.65 milliseconds. We can see this as each block in the background of the oscilloscope corresponds to 1 millisecond. And between each toggle there are around 6.5 blocks. After verifying in simulation and physically that the delay is 6.65 milliseconds, we use the formula 1 over t, where t is a delay, and we get a refresh rate of 150 Hz.
This test measures the latency of the input processing to the CPU, and we made this with some custom Verilog that we wrote. Each of the 10 buttons is its own test case, and when the button is pressed, the FPGA raises a flag signaling that the button has been received. On the oscilloscope, each square on the grid is 10 nanoseconds of latency, and we're measuring that latency by looking at the distance between when the blue input line starts to drop and the yellow FPGA line starts to rise. Here are the results of our button latency test. We had an average of about 12 nanoseconds per button press, which is a lot faster than we had anticipated. We can see that all of the buttons are under the 30 nanoseconds specification that we were hoping to achieve.